and then select all the balances that are less than 2500. So you can see that for both of those uh, queries, the end result would be the same. Right. Now, which one would be faster? This one or this one? Well, for this one, essentially, what are we doing? We are first getting the account table, projecting out the balance row attribute for all the rows. So that is now a smaller table. And then we need to select out all of the rows that have a balance that is less than 2500. The other one is we first filter out the rows and then project out all of the, so we have smaller rows and then project out all the balances, compared to we have all the values in the column and then filter out some of the rows. So in your opinion, I want some opinions on this. Which ones would you, out of these two, which one would be faster? The first one or the second one? Any clues? Should I be reducing the number of columns and then filtering out the values, or should I be reducing the number of rows and then projecting out the column? Well, take the second case, right? So first we are projecting out the balances. So we are doing some work on top of those all rows, right? We need to project out all of the balances. And then we are throwing away most of the work that we did because we are only selecting certain set of balances from there. We are throwing out the things that the project did because those balances are greater than or equal to 2500. Now the other one, the first one, we have to do a filter anyway to filter out the rows. The other one would actually not throw away any work that is done. It filters out the rows and then only projects out the balance. So in that scenario, we can say that this particular query would be faster compared to the other one, right? So in general, again, the heuristic example would be do your projects as late as possible. It doesn't always apply, but again, that's the heuristic, right? Okay, any questions on this? No? Cool. Okay, now, so we know that apart from select and project, the main thing that your database almost always has to do is to sort results, right? It needs to sort results to compare them. It needs to sort results to perform merge operations. It needs to sort results to make sure that your join operations are faster. It needs to sort results in order to perform grouping and aggregate operations. That makes your life much more easier, right? So there are different types of sorting algorithms available. So for tables that are small, your database can have different sorting algorithms in its toolbox. So for example, quicksort might be used to actually sort out your table that fits inside memory. But again, quicksort has its own disadvantages, right? So quicksort is not more efficient when your table is more or less already sorted, right? For that, you would need to use some more sophisticated algorithms. One algorithm that comes to mind is timsort. Timsort is nice. Merge sort for the merge operations is nice in another case, on the other hand, but timsort is nice. For tables that are, for example, larger than memory, that is where merge sort really shines, right? So what we can do is, given a large enough table, let's say 1 million or 3 million rows or billions of rows for that matter, what we can do is select part of the table, sort it, save it as a temporary table. Select part of the table, sort it, save it as a temporary table, and we keep on doing that. And then we can perform an n-way merge for all of those tables to get the final result, right? So that is an ability that merge sort gives you that quicksort does not, right? So that is why external memory sorting is really useful, because almost always, we are going to work with large enough databases, and a merge sort really helps us. So again, it depends, right? So if a database does not implement a merge sort and it has to revert back to quick sort, that is really slow. That is something that your planner needs to account for. So do I even do the sort in the first place? Should I just scan it in on the other hand to get my result? Because quick sort on a large enough database where data cannot be loaded into memory is really icky. Seriously, right? So we have to make considerations things about things like that. Okay. Um, in general, as for heuristics, sorting should also be, so we use sorting for order by results as well. But in general, sorting should also be applied as late as possible, because we want to be able to reduce the number of rows as much as possible. And then we can actually apply a sorting mechanism so that it does not take too much time. N log n is the best we can do. So it does not take too much time to actually sort out the results, right? However, again, that's a heuristic, right? For some operations, it might be beneficial to sort sooner, so to speak. For example, let's take grouping and aggregation operations, right? These operations would really benefit if my data is already sorted, because these operations would then become much more faster, right? Because grouping them, I can just sort out the results and then group, because they're already sorted. It makes my life easier to sort them out or aggregate them or things like that. So it depends upon what we are trying to do. And one particular module or one particular plan node can affect the efficiency of another plan node depending upon their ordering, right? If sorting is done before grouping, then grouping becomes faster. If grouping is done before sorting, then grouping is slower. And so sorting might be still be faster because we are reducing rows, but grouping is slower. So it has different sort of plans that we can actually look into and then essentially perform those things. Okay. Now, we also have join operations, right? So how do we plan on join operations? So join operations, as you know, are quite common in SQL queries. It is quite more common when we have normalized schemas. We have not talked about normalized schemas. We will talk about that maybe a couple of weeks from now when we talk about different normal forms and different types of formalities of normal forms. But in essence, it is a very costly operation, right? So we have this natural join operation on the attribute, some common attribute, right? That can be written as, for example, a Cartesian product and then select operation on the attributes, right? So R dot A equals to S dot A from that Cartesian product, then filter out all the results using that select operation. So what your database does, I mean, the simplest thing that your database can do is have a nested loop, right? For each tuple in TR, that in, in R, in the result R, for each tuple in S, we just perform a conditional check, whatever that condition might be, tr dot comma ts. So if they have to be equal, then tr equals to ts, and then add that to the final result, right? So that is what we do. We have a nested loop. We go through for each tuple in R, we go through all of the tuples in S. For the next tuple in R, we go through all of the tuples in S, find the one that matches, and then add it to our result, right? So this is a very simple strategy for your theta join. And you can see that this is sort of reminiscent of your file scan, right? So in the sense that it has to do it for all tuples. And secondly, this is also flexible. So it could satisfy any condition. It does not have to be an equality condition or anything like that, where indexes might be superior. It can actually apply this to any sort of condition whatsoever. So all databases, even though this is very inefficient, all databases would still have this strategy in their toolbox, like this simple joining operation, right? So sometimes a database might actually be small, or a table might actually be small enough to load it into memory. In those situations, it is quite slow, but it is not that bad this simple implementation is not that bad. For example, if we are able to load this entire table S into memory, then it can actually do things much faster. But even if it is not, remember that it can and it is able to handle arbitrary conditions, right? Now comes some interesting aspects. So that was for arbitrary predicates, but can we make our life easier for some fixed type of predicates? So we know that most join operations involve some sort of equalities, right? And we usually call them EquiJoints, right? If you remember, this has to be equal to that and so on. So EquiJoints are really neat because we can use indexes to actually speed up our table lookups. So instead of having a nested loop, we can say that for each tuple in R, we have, let's say, an index that is built on top of S. So instead of actually looping over the values of S, we can retrieve the tuple TS from S using an index. Right. Instead of scanning through all of the rows in my S table, we can instead build an index on table S and then retrieve that particular tuple using that index. It might still take a few lookups. If you remember the B tree, we said that for 50 billion rows, it might take about 4 to 5 checks to find out the actual result, right? Going one level at a time. But 4 to 5 checks is still much better compared to making 50 billion checks, right? So we can sort of use indexes to make our lives easier. And that is only possible when we have equality constraints for our join operations, right? The second thing is it is only possible for EquiJoints only and only if and only if an index already exists for those join attributes. And this is really important. If an index already exists, only then are we able to use that index to retrieve that tuple, right? Otherwise, we revert back to normal nested loops, right? Okay. So now comes the famous MySQL join operator, right? So MySQL join is essentially is going to essentially use nested loops, and there are other more cooler mechanisms to perform join operations, which we will talk about later. But MySQL uses nested loops, right? So it uses nested loops to figure out your join values, and it has the ability to have n levels of nested loops, and so it can join n tables at the same time. Basically n levels of this thing. You can imagine that this would be really, really slow, and it is, but MySQL still uses this because it optimizes the heck out of this thing, right? It basically has many clever optimizers on top of it that actually would order the tables that are being looped into, so that the internal tables are being internal in the loop nested loops. The internal tables are as small as possible so that they are being joined with larger tables to make sure that the results are smaller. It also uses indexes heavily. Whenever it is possible, it always tries to use indexes as much as possible to find tuples in the inner tables. So it optimizes the crap out of this thing and basically makes, even if it is a multiple nested loop for those join operations, it is still sort of fast, right? Um, well, I say it is fast for homework 4. Part A, you would see that some of the queries are not, right? Okay. So, so since